All right, hitting the home stretch now. Last video on t-tests before we move on to analysis of variance. Some new directions that I want to talk about. I always like to talk about new things that people are talking about. Sometimes people have the impression that statistics never change, which is certainly not the impression I have from working in the field for 25 plus years now. Statistics do change. They've changed a lot throughout my time in the field. So what are some of the new directions? Statistics actually develop rapidly. Here are the things that all the nerds are talking about right now. Instead of using P of 0.05, we found that through some simulation studies that actually probability of 0.05 is pretty weak evidence. In fact, one thing that we see is if the null hypothesis is actually true, values of P of 0.043 and stuff are relatively common. They're not particularly surprising at all. So that's one thing people are talking about. Statistics such as what's called the Bayes factor in place of a p-value, instead of a p-value or as a supplement to a p-value. Welch's adjustment to the t-test, using that kind of as a default setting rather than not using it. So P of less than 0.05. A pretty large team recently published a call to redefine levels of statistical significance at 0.005. A lot of reasons for this, but their primary argument is the false positive rate in psychology is way too high. And changing the criteria at which we could reject a null hypothesis will change that. We'll change that. We'll make fewer false positives. And they also suggest that this would greatly improve our ability to replicate studies. Psychology recently has gone through a bit of a crisis in that a lot of famous research studies are showing that they don't actually replicate when people try to redo them. Bayes factors. Bayes factors are statistics that assess the relative evidence for the null hypothesis versus the alternative hypothesis. They can be set up in two different ways. But when we have values, say, greater than 1, it suggests greater support for, say, the null hypothesis to the alternative. That's considered relatively weak evidence. 2 to 6 is considered positive evidence. More than 6 is considered strong evidence. One thing that's super cool about these is that with Bayes factors, we are actually quantifying how much support we have for the null relative to the alternative or the alternative relative to the null. When we're doing hypothesis testing, we can talk about being able to reject the null hypothesis, but we can't talk about being able to accept the null hypothesis. So Bayes factors is a way for us to have evidence for the existence of no effect. So that's a real improvement over what our null hypothesis significance testing paradigm gives us. You see that we can do this in R using a package called Bayes factor. There's certainly other packages that do this. The Bayes factor package, we simply feed it the command ttest bf, and you can see you have to give it a formula and the name of a data file, and then it spits it out for us here. It tells us here that our Bayes factor is 80.97. The way this one is set up is evidence for the alternative over evidence for the null. What's that saying? Well, the alternative hypothesis is 89 times more likely than the null, suggesting very, very strong evidence for the alternative hypothesis for there being an actual difference between our two groups. So recent work suggests that the Welch's t-test should be used as a default test. And I think I got this citation wrong. There's somebody who comes before Lockins on this. I apologize to them. The test adjusts for issues related to unequal variances. That is, having two very unequal standard deviations for your groups. that can actually inflate your chances of type 1 error. And what's nice in R is that it automatically does this. If I set this to false, it will not do the adjustment, and you'll see it gives me a certain result. But if I set it, oh, I'm sorry, if I set variance equals to false, what it will do is it will give me degrees of freedom equal 19.232. And I'm sorry, this is not a default in R. What is that degree of freedom adjustment doing? Well, that's how it's adjusting for this inequality. What that degree of freedom drop is going to do is it's going to make the probability go up, and it's going to account for that problem that happens when we have unequal variances, which is that our false positive rate tends to go up. So this is an adjustment that takes care of that problem. All right, with that, we have reached the end of the t-test.